Okay. Hello everyone. Good evening. So we were discussing 2018. Hello.
Hello, good evening, ma'am.
Yeah. Good evening. So we were discussing 2018 inorganic chemistry questions. So today we will start with
Ma'am,
yeah.
can I say, ma'am, schedule is still not updated. I just click on the link because I know the timing 7 to 8, ma'am.
Yeah. I know. I have mailed them regarding this. See why they have not. Not just for my class, actually for all the classes you can see in that NPTEL website.
Yes,
After
yes,
that, it's not updated. Yeah.
yes, ma'am. That's why, no? That's why I was continuously mailing you.
Yeah. Okay, no problem. Okay, then we will start discussing this question number 38 from Gate 28 in paper. The question is the second order rate constant for the reaction between CONH3 whole 5x N plus, where N is equal to 3 for X is equal to NH3 and H2O, and N is 2 for 2 when X is Cl minus, and chromium H2O whole 6 whole 2 plus at room temperature varies with the X as. So three options are given, three ligands are given. Like X is NH3 Cl minus or H2O, and we have to find out that the rate, the second order rate constant order for this reaction. Okay. So first of all, in this case, the what is the reaction they are asking for? Cobalt. There are five ammonia coordinated to this cobalt complex, and X is another ligand, and this is reacting with chromium H2O whole 6 2 plus. Okay. So anybody, what will be like? What will form after this reaction? Okay. So here, this is actually redox type of reaction. So this is a question from coordination chemistry, and these are. So here, what will happen is CONH3 whole 5 H2O, and now and plus it will be CrH2O whole 5. CrH2O whole 5, and one will be this X. Okay, just wait. I will disconnect this and connect again. This there is some problem. I will reconnect again. Okay. So here, the options are here. It is written that N is 2 when it is ammonia or H2O. Okay, and N is 3 when it is Cl. N is the overall charge of the complex. Now, how we have to see what will be the oxidation state for this. Here, one X is there. Okay, there is an X here. So, if we consider that X is the oxidation state of this cobalt, then X plus ammonia is a neutral ligand. So 5 into 0. And when it is water or ammonia, as water and ammonia are neutral ligands, it will be 1 into 0. Okay. So this is N. They have given for ammonia and water the value of N is 2. Therefore, for when X is NH3 or H2O, X is equal to 2. Okay. And now we will see for Cl minus case. This was when it is NH3 or water. Okay. So X plus 5 into 0 into Cl minus means it is carrying a negative charge, that is plus minus 1 is equal to 3. They have given 3, right? So X minus 1 is equal to 3. Did I say correct? I said just the opposite, right? For NH3 and H2O, it's 3. So X is equal to 3. And when it is Cl minus, N is 2. So here it is 2. 2. That means X is equal to 2 plus 1. That is 3. So the cobalt is in plus 3 oxidation state no matter what if X is NH3, H2 or Cl minus. Okay. And for chromium, X plus water is the neutral ligand. So 6 into 0 is equal to plus 2. That is X is equal to plus 2. So chromium is also in plus 2 oxidation state. Okay. And now if we come here, what will happen is here I said that redox reaction is taking place. So this cobalt will have an oxidation state of plus 2 and chromium will go to an oxidation state of plus 3. Okay. So here now it will be n plus 2 plus and that will be n plus 1. Right. So now we know that here this redox reaction is taking place. And redox reaction in coordination chemistry can take place via two type of reaction mechanisms. So in 2019 also there was a question from this topic, inner sphere and outer, like from this redox reaction in coordination chemistry. So that question was from inner sphere mechanism, and this also you can say that it is kind of exactly the same question only. Just the way they have asked is different. So there are, that's why it's important to solve previous year questions. So there are two type of mechanisms by which redox reactions can take place in coordination compounds. One is outer sphere mechanism and the other is inner sphere mechanism. So what are the general differences between outer sphere and inner sphere mechanism? In outer sphere mechanism, both the complexes, both the reactant on both the reactants which are present, both of them are inert in nature, whereas in inner sphere mechanism, one of the complex is inert and the other is labile in nature. And in outer sphere mechanism, there is no bridging ligand present. In inner sphere mechanism, bridging ligand is present. And in outer sphere mechanism, we can't see any ligand transfer, whereas in inner sphere mechanism, ligand transfer may or may not take place. But if we observe any ligand transfer is taking place, we can be sure from that redox reaction is going via inner sphere mechanism. Okay, so if ligand transfer is involved, that means that there is this reaction is definitely taking place by inner sphere mechanism. So now here we mentioned in one point that both the complexes are inert, and in this one is inert, another is labile. So labile, here I also want to say one point. It is that if it's not labile, like then it should be at least coordinatively unsaturated. Okay, so coordinatively unsaturated complexes are also considered as reactive, like as they are having unsaturation in their like they can accept more ligands, so those kind of complexes are also considered labile only. So now, coming to this, what is inert and labile? Okay, so comes from their kinetic stability. So here, the two complexes which are given are this cobalt complex and this chromium complex, and both are octahedral complexes, right? So it will be labile if the coordination number is less than 6, that is coordinatively unsaturated. And how we say it is inert or labile is that, so this is an octahedral complex, and in an octahedral complex, the ligands approach this metal center from the axis. Okay, so it approaches from the axis, and we know that in an octahedral crystal field, the degenerate d orbitals are split into how many energy sets? T2G and EG, right? So this T2G is having dxy, dyz, and dxz, whereas EG is having dx square minus y square and dz square. Okay. So why this T2G is lower in energy? Because as we said that in an octahedral crystal field, the in octahedral complexes, the ligands are approaching from uh, the axis, and this gx square and dz square are in this, the lobes are present on the axis, right? So if we consider xy and if we consider z here, so dx square and dz square are like this, whereas for dxy, dyz and dxz, the d orbitals, the lobes, they are present between the axes. So therefore, this because of this repulsion, this Eg is higher in energy, and uh, if there is any electron present in Eg orbital, it makes that complex labile in nature. Okay, so that is one case when the complex is labile. And also if we are having, let's say we are having a D1 system, so D1 system is also labile because there is like place to, here this is also not completely filled, this T2G is also not filled, so electrons can come to into these two orbitals as well. So D1, D2, these two systems are labile in nature. Okay, and whenever there is electron present in Eg orbital, if electron is present in Eg orbital, that complex is labile in nature. Okay, so D1, D2 is labile, D3, 1, 2, 3. D3 it's not labile. Okay, all the three electrons are filled in T2G orbital, whereas in D4 there are two possible ways, right? If it is a high spin complex, it will be like this, whereas if it is a low spin complex, it will be like this. So this low spin, this one is this one is inert in nature, whereas this complex, as in Eg orbital electron is present, this is labile in nature, and so on. It will, like, I think you got it. So D5,
Ma'am,
yeah.
ma'am, please repeat from where you told two energy sets T2G and EG. One quick revision, please.
Okay, so it will split into two energy sets, T2G and EG. So in T2G, we know that T2G has dxy, dyz and dxz orbitals, whereas EG is having dx square minus y square and dz square orbitals, right? And in octahedral crystal field, the ligand approaches the metal from the axis. Okay, so whenever there is electron present in the axis, that is in that Eg orbital, as they are in Eg orbital, we can see that this dx square minus y square is like this, and the z square is like this. That is, the lobes are present on the axis, right? So whenever electrons are present in that Eg orbital, they are labile in nature. Okay, Whereas if it is present in T2G orbital, it is inert. But if we are having only one or two electrons, then there is one completely empty space here also. So they are also considered labile. Okay. So D1, D2 system is labile in nature. D3 is always inert. D4 will be, if it is high spin, we can see that there is one electron in the EG set. So it is labile in nature. Whereas if it is a low spin complex, all the four electrons are in T2G set and this is inert in nature. And same goes for D5. If it is a high spin complex, it is labile in nature. Whereas if it is a low spin complex, 1, 2, 3, 4, 5, it is inert. For D6, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So high spin means it is labile, whereas low spin means inert. But for D7, D8, D9, these complexes, it will be always labile, right? Because there will be electrons in each set. At least one electron in each set, whether it is high spin complex or low spin complex. Okay.
Okay, ma'am.
Okay. So, so this is the concept of this. So now we will see that this cobalt 3 plus is how many electron system? It is a D9 system if it's cobalt. Okay, so cobalt 3 plus means it is the D6 system, right? And there is NS3. NS3 is a strong field ligand or weak field ligand?
Weak field ligand.
No, ammonia is a strong field ligand. Okay, so ammonia is a strong field ligand, and because of that, it will be a low spin complex. So 1, 2, 3, 4, 5, 6. It is inert in nature. Okay, this first complex will be inert in nature, and the second one, that is the chromium 2 complex. Chromium is a D5S1, right? D5S1 means it is a D6 system, but chromium is in plus 2 oxidation state. That means it is a D4 system, right? And D4 system, water is a weak field or strong field ligand?
Ma'am, weak field ligand.
Yeah. So here, in electron is present in EG set, therefore it's labile in nature. Okay, and it is a high spin complex. So in this case, we can see that one is labile and one is inert, and also this X is getting transferred here. So in this case, you can also think in this way that here just the reactants are given. So how to know whether it is, and they are asking for inner sphere mechanism, asking the reaction via inner sphere mechanism or outer sphere mechanism. So one point is this, that we saw that in this case one is inert in nature whereas one is labile in nature. This satisfies this inner sphere mechanism wala thing, and also in in inner sphere mechanism, here in the question they are asking the second order rate constant. Okay, so in inner sphere mechanism, what happens is we are having, say I am taking the first metal as M, one is cobalt and one is chromium. I will write them as M and M dash. Okay. So what happens here is ML6 is there and M dash L dash 6 is there. So sorry, it is ML5. Right. In one case it is ML5X. So ML5X and M dash L6 dash. Actually here, see, in our, this is I am showing you the mechanism for inner sphere. Okay, so in inner sphere, what happens is, here we can see that one is labile. So what happens is, it will first release one water from it and it will become chromium 2 H2O whole 5 2 plus. Okay, so after that, this is taking place. Here, from here, already one L dash is gone. Now it is M dash L5, L dash 5. Okay, so first this thing is taking place. Okay, Then next, electron transfer is taking place from, let's say, okay, so this is in plus 2 oxidation state and this is in plus 3 oxidation state. Then what will happen is M dash L dash I. Okay. Now this will go to plus 3 oxidation state and this will go in plus 2 oxidation state. So here electron transfer is taking place via this bridging ligand. Okay. So it is giving one electron to this and via this bridging ligand it is transferred in onto the other metal complex. And then finally we will get Ml5 plus M dash L dash 5 X, and here one L dash was there, so this will react with this L dash to give Ml5 L dash. Okay, so these will be the two products after redox reaction. Whereas in, so here the rate constant, here the rate depends on both this reactant, reductant and oxidant. That is,
Ma'am, last step.
yeah, I'll coming back to that again. This one. So here you see, first this ligand, this X ligand, the bridging ligand was present, was coordinated to this metal M. Okay. So first what is happening is, this is coordinating, this is making this interaction with this M dash L dash 5 as well. And then via this bridging ligand only, the electron transfer is taking place from this metal center to this metal center. Okay, and now what is happening is, this bridging ligand, in this process only, the bridging ligand is dissociating from this metal complex and it is coordinating with the other one. Okay, you can see this dotted dash bond here and this solid bond here. Then after that, finally it is dissociating. Okay, to get the redox reaction products. This is the final step is dissociation. So it is, now we are getting Ml5 and M dash L dash 5 and this X, this bridging ligand will now come onto this side. Here you can see this. Okay, first this was present with this X, cobalt. Now it is with this chromium, right? So, and this now as it is coordinatively unsaturated, this L dash ligand was there in the reaction media. This L dash will react with this Ml5 and we will get Ml5 L dash. Okay, so this is how inner sphere mechanism takes place and the rate of this rate will depend on both the oxidant and reductant, and it is second order, it is first order with respect to both the reactant and oxidant. So this is a second order reaction. Okay. Whereas in outer sphere mechanism, how it takes place is, we are having Ml6 and Ml M dash L dash 6. Okay. Here also we get the same product after that, but here bridging ligand is not present. Okay. So after the reaction, we will get M. If it was 2 plus and 3 plus here, after the reaction, it will be 3 plus and 2 plus. And here, this kind of thing is not taking place because here no bridging ligand is present, and electron transfer takes place from, they will also not form any such kind of coordination there. Okay, so the two complexes will be present just like that. First, there will be some interaction between them, and it will first form the precursor complex. Okay, and then elongation or activation takes place. The bond lengths, like they get changed, and this electron transfer takes place when both of them are present in two different coordination pairs. Okay, so that activation step takes place, then this successor complex is formed. Okay, so this is how outer sphere mechanism takes place. But the second order rate constant is for, so in outer sphere mechanism, what happens is this formation of precursor complex and successor complex is fast, whereas this that activation step that is slow. So it is not giving a second order rate constant. It does not give a second order rate constant. So that is another point how we can understand that it is going via an inner sphere mechanism. So if we go to the question, here we can see first of all that here one different ligand, this X is given, and in this option we can see that the Cl minus is also given here, and Cl is a bridging ligand, whereas and also we can see that this is they have given second order rate constant, and we saw that among the two complexes which are given in the question, one is labile in nature and the other one is inert in nature. So here they are asking us the second order rate constant, that is a rate constant for when this reaction is going via inner sphere mechanism. Now, as we already told here that if bridging ligand is present, then the reaction is much faster as it helps in transferring the ligands. So, among the given like X is either ammonia, water, or Cl minus. Among these three, only Cl minus is a bridging ligand. So for Cl minus case, the reaction will be fastest. Okay. So when Cl minus is X, then by inertia mechanism, it is transferring that bridging ligand is transferring the electron from one complex to the other metal complex, and it is fast. But for H2O and NH3, it is not the case. They are not bridging ligands. So what happens is, now we have to see that which one is more inert in nature. So if we know the spectrochemical series, right? In spectrochemical series, we know that ammonia is a strong field ligand, whereas water is a weaker field ligand, right? And this delta O value, what is delta O value? This is T2G and EG in octahedral crystal field. Then the difference between this energy gap between this T2G and EG level is the crystal field splitting del O for this. And if del O is more, then the complex is more inert. Okay. So for NH3, when X is NH3, then this CO NH3 whole 5X N plus, this complex is more inert. Okay. And if it is more inert, then it will be less prone for it to take part in the reaction, right? So for NH3, it will be the least, it will have the least rate, and H2O will be in between. So for this question, it is the second order rate constant for the reaction between CONH3 5XN plus and CrH2O whole 6 2 plus at room temperature varies with the X, as the maximum will be for Cl minus followed by H2O, and it will be least for NH3. So this will be option number B will be the correct option for this question. Is it clear?
Yes, ma'am.
Okay. So Shikha, actually you missed, I think, those classes. There is one YouTube channel also. Since the recording links are not yet available in the website, you can search Riturani Mandal in YouTube. Those video links are only given in the NPTEL portal. Okay, recording link, class recording link. So you can go to that. After every class, I update that. So when I solved this 2019 question, that day I discussed about this thing. Okay,
Okay,
so
ma'am.
you can see that.
Ma'am, I
Okay.
think last week one question was also pending, na?
That CS3OI, that thing, right? Rhodium,
Yes,
that
ma'am, that
complex.
was,
So
na?
it was actually a direct question from Monsanto acetic acid process. Okay.
Okay.
So I will discuss the other questions, and at last I will discuss about that. Okay.
Okay.
This question only took much time. So now we will move on to the next question. So the next question is question number 39 from 2018 paper. The question is, for the following reaction sequence, this is the reaction sequence which they have given, and they have asked that what is X and Y for this reaction. So here ammonium chloride, it is reacting with, wait, so 3NH4Cl is reacting with 3 boron chloride, boron trichloride, and first they are giving heat and C6H5Cl. So this C6H5Cl is a chlorinating agent. And this, if you know about borazine, this is actually this is also type of a direct question. If we know that what are the different procedures for synthesis of borazine, borazine is also known as inorganic benzene. So this is also an important concept. You can People can go through this borazine once. It is also called inorganic benzene. Okay. So benzene, why inorganic benzene? Because in benzene we know that it is like this, and borazine is, okay. This is inorganic benzene. Right? Here it was C6. Benzene is having C6H6 where it is, whereas this is B3N3H6. Okay, where B and N are present in the alternate positions. So this is one of the way for synthesizing this borazine. So we will see how it is forming. First, in first step, what they are doing, they are adding C6H5Cl and heat. So this is a chlorinating agent. What will happen? First, it will form Cl3, B3, N3, H3. Okay, and then there two, it is they are treating it with LiBH4. So LiBH4 is a reducing agent. Okay, so LiBH4 is a reducing agent, and that's why it is removing this HCl, and we are getting B3N3H6. So this is nothing but borazine. Okay, so X is B3N3H6. X is B3N3H6. Now, in the next step, what they are doing, they are adding 3 equivalent of water into X at room temperature. So, and here this is having delta H, H, delta minus, delta plus, delta minus, delta plus, delta minus, delta plus. Now they are adding 3 equivalents of water at RT. So we know water is having H plus and OH minus. Therefore, what will happen is it will form B3N3H6 and then 3H from this 3 water. Sorry, 3 water means 6H, right? And 3 OH. So it will be B Okay, H, either it will be here or there, like BH3 and H2, H, H, H. So here they are actually not asking about the structure of this compound. They are asking it in this form, right? So this we can write as B3N3. Then what I said here. There were already six hydrogens present that will remain the same, and we can check this 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And OH is also 3. So now in the options we have to see one is X is B3, N3, H6, and Y is B3, N3, H6, H3, OH3. This is Y. So here they have given it like this BHNH whole 3 and this. So if we break this, what will be this? H3, B3, N3, H3. Right. That is nothing but this, just they are trying to confuse B3, N3, H6. Okay. So in A and B, it is given B3 and 3H6, that is the inorganic benzene or borosine, but in C and D, the X is something else. So we can just eliminate these two options and then we will see this one. So this H2O, H plus and OH minus it is coming now. So we will see here H, OH, B, NH2, and this whole thing is 3. So H3, OH3, B3, N3, H2 3 is 6. That is what we say this one B3, N3, H6, or total we can write as 9, and OH3. So whereas here it is given as NH2OH, but H2O will give H plus and OH minus, and H plus will coordinate with N or B. This H plus and OH minus is coordinating to nitrogen or boron. Okay, but here they have given as NH2OH. So option number A will be the correct option for this question. It is for the given reaction sequence, X is HBNH whole 3 and Y is HOHBNH2 whole 3. Okay. So if you know about the synthetic methods for the preparation of borosine, we can solve this question very easily. Then we will move on to the next question. So it was clear?
Yes, ma'am.
Okay. So we will now discuss question number 37 from the same paper. The question is, generally the coordination number and the nature of electronic absorption band, that is F to F transition of lanthanide 3 plus ions in their complexes are respectively option number A greater than 6 and sharp, option number B 6 and broad, option number C less than 6 and sharp, option number D greater than 6 and broad. Okay. So in lanthanides, so we mostly discuss about this transition elements, like right. In transition elements, we have seen what happens? D to D transition takes place, right? D to D transitions take place, whereas in lanthanides, we see F to F transition taking place. Lanthanides are also known as inner transition elements. So in these cases, we have seen that for the G block elements, the maximum this coordination number is 6, right? It can be tetrahedral, square planar, or sometimes the maximum coordination number which we mostly see for this D block elements is 6. But the lanthanides are bigger in size. Okay. And so this is for D block elements. If we are considering this as a stair, but for lanthanides, this thing is big as compared to the D block elements, and hence it has more space, and hence it can coordinate to more number of ligands. Okay, so the coordination number for lanthanides is actually more than 6. It will be greater than 6. Sure. For example, this is one complex, this cerium complex. Okay, cerium is having, this is not a yet, but there are complexes in which this lanthanides are having coordination number of 12 as well. Okay, so lanthanides, because of their bigger size, their larger size, they can have a coordination number of more than 6. So we can eliminate two options, that is less than 6 is not correct, and the 6 and broad is also not correct. Now moving on to the nature of the electronic absorption in this FF transitions. So as we already said that these are inner transition elements, right? Lanthanides are inner transition elements, that is, in these cases the electronic configuration is like we are having this 3d10, then say 4s2, and then 4f. Electrons are present in the 4f orbital, right? Whereas this 5d, this is not filled for plus 3 ions, 5d and 6s. So we can say that this f orbitals are deeply buried inside. Okay, they are deeply buried inside. And what happens for this DD transition is that since there, if we consider the metal ions, what happened is there were systems like 3d2s1, and let's say when it was present in plus 2 oxidation state, it will be D7 system. So here it was the outermost orbital shell. So what happened is that d orbitals can directly interact with the ligand. As we discussed that ligand approaches from this axis and all those things we talked about. So what happens in DD transitions is that ligand can directly interact with the metal orbitals, and because that is the reason for which we get broad transitions, we observe broad transitions for DD transition. Okay, the spectrum is broad, whereas since F is deeply buried inside, okay, so here there is no direct interaction between ligands and the f orbital. And because of this, only the FF transition spectra which we see, it is sharp. We get peak like this, whereas for D we will have something like this. Okay. So you can go to that GATE NPTEL portal, and there is a video. If you go to that GATE syllabus mapping, okay, and click uh, go to lanthanides. In periodic properties, you will get a video from Professor D. Rai. There he has discussed about the periodic properties of lanthanides. Okay, so for to know more about this, you can go through that. So for this question, the coordination number for these lanthanide 3 plus ions are, they are greater than 6 and they are sharp in nature. So greater than 6 and sharp, option number A is the correct option for this question. Okay, we will move on to the, it's okay. Is it clear?
Yes, ma'am.
Okay, so we will move on to the other question from 2018. So this is question number 40 from GATE 2018. For an inverse spinel AB2O4, the A and B respectively can be, four options are given. Option number A, nickel 2 plus and gallium 3 plus. Option number B, zinc 2 plus and iron 3 plus. Option number C, iron 2 plus and chromium 3 plus. And option number D, manganese 2 plus and manganese 3 plus. So nickel 2 plus is how many electron system? D8, right? So it is a D8S2 system, but as it is given in +2 oxidation state, so nickel, here we will write nickel 2 plus. First we are talking about this. So this is a D8 system. D8 system means, okay, so first about this normal, inverse and mixed spinor structures. So we know that if A2 plus is going to the octahedral void, sorry, A2 plus is going to the tetrahedral void and B3 plus is going to the octahedral void, then we will get a normal spinor structure. Okay, that is, this we can also say that if we are having a smaller ion, compare two ions which we can compare, if the smaller one is going to the tetrahedral void and the larger one is going to octahedral void, then also we will get this normal spinor structure. And how we can find out? We can find this thing through CFSE calculation. So if A2 plus CFSE, A2 plus in octahedral crystal field, if A2 plus CFSE is less than B3 plus crystal field stabilization, CFSE means crystal field stabilization energy. Okay. If this is the case, then we will get normal spinor structure. Whereas if A2 plus octahedral crystal field splitting energy is greater than B3 plus octahedral crystal field stabilization energy, then we will get inverse spinor structure. And there are cases in which we will get a mixed spinor structure. When the CFSE, they are coming out to be same and also they are having comparable sizes, then we get this. Okay, I will write mixed is same CFSE for both this A2 plus and B3 plus and comparable size. So in this case, we get mixed spinor structure. So here we have to answer which one will have an inverse spinor structure. So for inverse spinor structure, what we need, this A2 plus in octahedral crystal field, this crystal field stabilization energy should be greater than for B3 plus, right? So let's see for the first option, nickel 2 plus, that is G8 system. So 1, 2, 3, 4, 5, 6, 7, 8. And also this we should know that 3, 4, 5. This is minus zero point 0.4 del O and min for plus zero point 0.6 del O. EG set and T2G set. So here the crystal field stabilization energy will be CFST is equal to mod of minus zero point 0.4 into how many electrons are available in this T2G set? 6, right?
Yes, ma'am.
Plus plus zero point 0.6 into 2, that is minus 2.4 plus 1.2, which is equal to minus 1.2 del O. Okay, then going on to this gallium 3 plus complex, right? So gallium's electronic configuration is 3d10 4s to 4p1. Okay, so 3 plus means it is a 3d10, it is a d10 system. So for this one, the CFSE will be 2, 3, 4. It is completely filled, right? And if it is completely filled, that means for minus zero point 0.4 into 6 plus zero point 0.6 into 4, that is equal to minus 2.4 plus 2.4, which is equal to 0. So crystal field stabilize. In this case, we can see that nickel 2 plus is having a greater CFSE value than gallium 3 plus. So this option is satisfying the condition for getting that inverse spinor structure. So now we will also check the other options which are given, Zn2 and Fe3. So Zn2 plus. Zinc 2 plus is also a D10 system. So CFSC will be 0 and Fe3 plus means Fe is actually D5S2, right? If it is D3, then it's G6S2. Fe3 plus means G5 system. 1, 2, 3, 4, 5. So minus zero point 0.4 into 3 plus zero point 0.6 into 2. That is minus 1.2 plus 1.2, which is equal to 0. So I think we know by this time that the CFSE value for D5 and D10 configuration complexes, they are always 0, right? So in this case, what we saw is for both the CFSE is same, right? Here for both CFSE is same, but we know that if we go along the series from left to right, then the size decreases. Okay, so zinc is smaller in size than Fe3 plus, and zinc is in plus 2 oxidation state. So the smaller one is going to the tetrahedral void, and the larger one, that is Fe3 plus 1, the trivalent ion, that is going to the octahedral void. So that will go to the octahedral void. So it is also having a normal spinor structure only. It will have normal spinor structure. Then the third option is Fe2 and Cr3. Fe2 plus. So Fe2 plus is a D6 system and chromium 3 plus. Okay. So Fe2 plus means D6 1, 2, 3, 4, 5, 6, that is minus zero point 0.4 into 4 plus zero point 0.6 into 2, which is equal to minus 1.6 plus 1.2 or minus zero point 0.4 del O. And for chromium 3 plus, chromium is G5S1. So chromium 3 plus means a D3 system. 1, 2, 3. So minus zero point 0.4 into 3 plus 0, which is equal to minus 1.2 del O. So chromium 3 plus is greater than Fe2 plus. That is B3 plus CFSE is greater than A2 plus CFSE. So it will have a normal spinner structure. And the last option, that is manganese 2 and manganese 3. Manganese 2 and manganese 3. So manganese 2 is a D5S2, 3D54S2. Okay, so manganese 2 means it is a D5 system. D5 system means crystal field stabilization energy is 0. We saw that already. And manganese 3 means D4 system. So 1, 2, 3 and 4. That is minus zero point 4 into 3 plus 1 into zero point 0.6. That is equal to minus 1.2 plus zero point 0.6 or minus zero point 0.6 del O. So in this case also Mn3 plus is having a greater CFSE value than Mn2 plus. Right. So this is normal spinel or inverse spinel? Normal, right?
Normal spinel.
Yeah. So among the given options, we saw that this B, C, D, they are having normal spinel structure. Just for this option number A, that is nickel 2 plus and gallium 3 plus, we are getting an inverse spinel structure. So for question number 40, the correct option will be Ni2 plus and gallium 3 plus. Okay, it's clear?
Yes, ma'am.
Okay. Now about that question where we are having doubt. So these are few of the processes in as organometallic chemistry. That question, that rhodium question, it was from, that is a direct method for the synthesis of acetic acid from methanol. Okay. So what actually happens is we are having methanol, then HI, CH3OH plus HI. This will give us CH3I. Okay. And then this CH3I will react with, this is the thing, RH, I, CO, CO, and overall negative charge on this complex. Now this CH3I and this will react, and what will happen? First oxidative addition takes place. Oxidative addition takes place to give this I, 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 CH3, CO, CO minus. So the question was given from this. Okay, right? We were given this thing. The question, in the question, the complex which was given was this. And then what they said, that at high temperature and high pressure, another CO molecule was inserted. So what happened initially? Migratory insertion took place as carbonyl ligand is present, and CH3 type of ligand, they can insert into the carbonyl ligand, and we will get COCH3. So in first step, this is taking place. This will also have an overall charge of minus, and then this CO ligand. Now it is having a coordination number of 5. So now CO can got a space to coordinate to this rhodium, and we will get rhodium I, I, CO, COCH3 and CO. Okay. And from here, this reductive elimination takes place to give CH3COI, and this CH3COI will further react with water. So how water is coming? Because it came in this step. Okay, here H2O was releasing. So let me draw it. This H2O was there, it gave CH3COOH. Okay, and then again this whole thing will take place. So this is the whole Monsanto acetic acid process. So I too forgot about this thing. So this was actually a direct question from this process, and this is a well-known way to synthesize acetic acid from methanol. So the CH3COI, the release of this is more prone. That means because this is used as an industrial process for making synthesizing acetic acid. So anything else from today's class or earlier classes?
No, ma'am. Thank you.
Oh, okay then. Thank you.